Hello everyone. So in this lesson we're going to talk about some properties of sound waves. Now as we remember from previous lessons, sound is a longitudinal or compressional wave, and that wave travels through, generally speaking, the air. It can also travel through water and solids and other media, so to speak, but in this lesson we're going to focus on how sound propagates through air. Now, in the lab we did the other day, we got to play with some slinkies, and we were able to create a longitudinal or compressional wave in a slinky in a couple different ways, but essentially what we were doing, right, is we were bunching up the coils, like so, and then releasing that bunch and allowing it to traverse the length of the slinky. And we saw that that compressed area of the slinky, it expanded a bit, but overall, you could watch that compression wave move down the length of the slinky. Now, the analogy here that we're drawing is that in air, with sound, what happens is we have an event that creates a sound wave, so it compresses a region of air, right? And this is my region here. This is a compressed region of air. So compare that, right, between our normal air out here. It's compressed. There are more particles in it. And what happens is, after we compress, right, maybe we clap our hands and we compress an area of air, that compression will move along sort of the length of air or through the air. And additionally, in our slinky, right, we were able to see areas here, right in the middle, where the spring maybe got stretched out beyond the normal stretchedness of the spring. And similarly, we can see those in air too. And of course the name for these are rarefactions. So in a longitudinal or compressional wave, we alternate between normal areas, compressed areas, and rarefied areas. And rarefied just means, think of it as rare, right? Less air in that area. It's more spread out. So that's a rarefaction there in the middle. And on the sides here, we've got our two compressions. So this little diagram, I sort of drew a tube, but essentially I'm just showing you a cross section of the air, right, when we've got sound waves moving through it. Okay, excellent. So that's our basic analogy here, right, which is that in a sound wave moving through the air, something compresses the air in a localized spot, and then that sound wave will move, right? And that compression will move, pushing sort of, the particles will compress, they will then expand and rarefy, and that's how the wave moves from the point of origin to everywhere else around it. So this is something that the book hasn't really talked about, and we haven't either. When sound is created, it spreads out in all directions, and I really mean all directions, as much as it can. So if you were to somehow create a noise in the middle of a room, it would spread out actually in a sphere, right, in 3 dimensions. That compression would expand and spread out. So what I've drawn here, a little hard to draw spheres, so I'm sticking to 2 dimensions, but you can see I've drawn rings of concentric circles expanding out from our noise source. So in this case, our noise source is our little drum major here, and he is beating the drum. And when he hits that drum, the surface of the drum vibrates, and that localized vibration compresses and rarefies the air around it, and that creates the waves that are expanding out from that drum. So one interesting property of waves, and this is true of all waves, not just sound, is that waves diffract. And what diffraction means is, so the waves are expanding outward from the source. And things get interesting when we hit an obstacle, right? And in this case, our obstacle is a wall. And I've just drawn this wall with 2 different sized openings. So by the time the wave has reached this wall, in this example, you can see it's not quite, but more or less parallel to that wall. And so the sound wave hits the wall, and a chunk of it, right, gets blocked, right? And then, that's kind of, it actually will reverberate back out, right, similar to the way we saw the slinky move, right? We would send a wave down the slinky, and when it hit a fixed point at the end, it would actually bounce back and reflect. But what we're interested in is what happens to the sections that go through the opening. Now, with our larger opening, we see that we've got, a fairly large chunk of this almost sort of parallel flat wave. And what happens with the larger opening, and when I say larger and smaller, this is all relative to the size of the wavelength. So in this case, the wavelength and these openings are sort of in the same size class, if you will. So, we get interesting interactions, right? If this, hole in the wall were huge, maybe hundreds of feet wide, we really wouldn't see any diffraction at all. So it's all relative to the size of the wave. But anyway, so what we see here is as the wave chunk passes through this hole in the wall, right, in a larger hole, the wave maintains more of its original curvature, right? So when we looked at the wave before it hit the wall, it certainly wasn't flat, but it was flatter than, the waves coming from the drum major right there at the beginning. And with a larger opening, we can see that we preserve more of that, I don't want to say flatness, but more of that less acute angle. And that's not to say that the wave isn't going to sneak around the corners like this, right? Because as soon as you reach, right, these corners, right, and you're compressing the air in here, the air is going to then sort of push that wave out in that direction. So I don't want to say that it's not going to sort of bend around the corner like that, but what I just want to point out is that in our large opening here, the shape of the wave is more preserved, right, as compared to our original one. Now, things get interesting when we look at our smaller opening. So in our smaller opening, right, we get only sort of a small chunk of that, larger wave passing through. And so what happens is the ratio between essentially the width of the opening, which is the width of sort of the preserved chunk of the wave, and the size is a lot smaller. So what happens is, maybe right in the middle, right, we still sort of preserve that curvature, but right at these corners, right, we've got air pushing, right, compressing outward. And so the net effect is that it's almost as if our drum major were in fact standing right at that little entrance there, that little opening, and playing there, right? The waves actually look very similar to the ones that we can see back over at the beginning, over by our drum major here. So anyway, so the general message here is that when a wave reaches an obstacle and there's an opening in that obstacle, if the opening is small relative to the wave, then we get diffraction, which is as if we had a point source of sound right at that opening. So let's look at another example of diffraction. So a megaphone. So you're probably familiar with what a megaphone is. A megaphone is an example of diffraction. So take a look at this. What's happening is I'm speaking here, and I create noise, and then it exits my mouth. And without the megaphone, right, that sound, just like our drum major, is going to spread out in all directions, right, from the opening of my mouth, because there's nothing sort of blocking it. Now, if I were to hold a megaphone a certain distance from my mouth, so some of the waves, some of the sound waves are going to enter that opening, and that's a small opening relative to the size of the wave, right? So what happens is, similar to our small hole in the wall there, right, we see the sound wave travels through the opening, and then once it reaches the other side, it's going to diffract out, right, in all directions from that source. Now, this isn't the full explanation for why a megaphone, makes me louder. There are a couple other reasons that we can't explain right now. But you can think about intuitively, right? If I were to hold the megaphone right up to my mouth, right, the sound waves, the energy, right, would all be going into the megaphone. It wouldn't be spreading out, right, in all these different directions. It would all be going into the megaphone. And so more energy, right, that's going to increase the amplitude of those waves. And additionally, right, as those waves are traveling the length of our megaphone, they can't escape outward, right? They can only go, directly to the other end of the megaphone and out there, right? There's nothing coming out here or here. So that means that, those sort of echoes and reflections that we would get off of the sides of the megaphone, the interior sides, all sort of bounce back and continue outward. And as a net result, we get a nice, loud, focused sound. So, moving on now to some other properties. So here, we've got some cylinders and some air. So once again, I've drawn air here, the little molecules in the air, and that's kind of the average density that you see there. So, what we're discussing now is, well, sound is vibrations, right? Vibrations in strings, right, create vibrations in the air, and those vibrations are these sound waves. So what happens when we have a column, right, a fixed column of air, unlike just the open air in a room? So as we said earlier, in the open air of a room, I create a sound, and that sound spreads out in a sphere, right, in a three-dimensional sphere. But what happens if I compress air, if I create a sound wave in a tube? It doesn't have the same freedom, right? It can't escape along these sides. So we get some interesting effects here. So take a look at this. So if I blow air across the top of this cylinder, right, I'm forcing air molecules out of my mouth, right? And that's going to cause a compression in this end of the cylinder, right? So we are pushing air molecules in, and we get this compression effect. Now, what's going to happen, though, over time is that compression, right, is going to want to move, right? That wave is going to want to travel, right? It's going to travel down the length of the cylinder. And so what we get is we then get a compression on the other end. And then it's going to travel back and form a compression on the other end, back on the original side. So this is a longitudinal standing wave. Now, in one of your previous videos, we tried to visualize this, and it was a little hard. So that's why I've sort of drawn all these little air molecules. But even still, it's a little difficult to see what's going on. So what we're going to do is use a little visualization trick where we will draw in a transverse wave, which we're more familiar with, right? That's what we are creating with our slinky. And that transverse wave will be a little visualization trick to help us better understand what's going on here. So what I'm going to say is, wherever I have a compression, I'm going to call that a crest of my transverse wave. And wherever I have a rarefaction, right, one of these empty regions here, where the air kind of is pushed out, that's going to be a trough in my wave. So what happens then, if I draw this, is I get, on this top one, on the left side, I've got a crest, and on the right side, I've got a trough. And now if I go and draw that in our t equals 1, right, so now we've got a trough on the left side and a crest on the right. And once again, if I go and draw that in here in t equals 2, we're back to our original position. Back to our original position, you say. That sounds like a standing wave. So now, if I sort of just complete this, right, to have our little diagram here. So essentially what we've got now is, you can see visually that this looks, now that we've used our little trick of turning it into a transverse wave, this looks like what we were creating with the slinky, right? And now we can use our vocabulary to say, aha, that right there is a node, right? That's a spot where we don't get movement. And if you look at that spot across these three cylinders, right, and you compare it to our outside air, right, the density looks approximately the same. And also, it's not changing, right, in any one of these. So that is our node, right? That's where no movement is occurring. Now, on the other hand, if we look at these ends here, right, these ends go from compressed to rarefied to compressed, right? And in this case, rarefied to compressed to rarefied again. So that's where our maximum movement, right, our maximum flux is happening. So those, using our vocabulary from before, are antinodes. Okay, so now that we've seen what happens in an open-ended tube, an open-ended cylinder, we're going to do the same little visualization trick with a closed-end cylinder. So this cylinder has one end open and one end closed, and you can see that I've shaded in black the closed section. So if we blow across the top of this, right, we are going to compress the air in that end, and that compression wave will, travel back into the cylinder. But, right, it's going to come up against this end here, and the wave can't travel any further, right, because those molecules, those little particles, are just going to bounce back. So the net effect here is that we get compression and rarefaction, right, on the ends here. But in this other end with the closed end, we just see that the density stays the same as the outside air, right, because that wave can't travel any further, right, it can't go anywhere. So what we do now, if we use our little visualization trick where we pretend a compression is a crest and a rarefaction is a trough, we can draw in on this wave, right? We've got our crest there, and then on t equals 1, we've got a trough, and then t equals 2, we've got another crest. So now, if we sort of draw the full picture, right? So that also looks like something we might have created with the slinky, but it's different from the one on the last slide, right? It's less steep, it's less radical, and that's going to mean a difference in the wavelength. So now, to wrap things up, what I've done is I've drawn both cylinders again without the air this time, just for simplicity's sake. So I've just got the cylinders and the transverse wave equivalent of what's actually happening. And now what we can do is continue our little visualization trick of drawing in this transverse wave, and to help us figure out how long the wavelength is, right? We know the length of the cylinder. That's some arbitrary length L, right? We can measure that with the meter stick. But we want to find out what the relationship is between the length of the cylinder and the wavelength, right, of the compressional wave we're creating. So what we're going to do is continue our little wave out beyond the reaches of the graduated cylinder. And I can do that on the other end here too, because, right, once again, this is open at both ends. So now that we've continued this wave out, right, it's going to be a little easier to see what's going on. So we know that a wavelength is the distance from one trough to the next trough, or one crest to another crest, etc. So if we trace from this end, so that's our trough, we go up, we go down, bingo, another trough. So now, if we go here, we say, okay, great, one trough to the next trough, that is lambda, that is our wavelength. And so now we say, well, what's that with respect to L? So if we do sort of mark the ends here and mark the middle, we say, ah, look at that. It looks like lambda is twice the length, right? It equals twice the length of the cylinder, right? Because half of the wavelength is contained inside the cylinder. Now, if we do the same trick with our closed-end cylinder, and I apologize, I'm going to erase that, give myself a little more room to work, and I'll write it back down later. So this time, right, that wavelength is, it's a lot longer, right? Okay. And now what we're going to do is we're going to trace out again a wavelength. So in this case, since we have to trace from the closed end, we're starting at a node actually, but it will start and we'll go down. So we go down from the node into a trough and then up and then back down again. And so now we've returned to an identical spot in the wave. So that whole length is lambda. And now if we use our little sort of visualization trick of drawing again. And unfortunately, this sort of second half of the wave isn't quite as long as it should be. But you can probably still see visually that we've got 4 chunks here. And so L is, right, it's that first chunk of the wave. So therefore, we have lambda equals 4 times L. So now what does this mean, right, in terms of the sounds that we're actually going to hear from these? So let's recall our all-important relationship between the different properties of a sound wave. So V, our wave speed, equals lambda times F, our frequency. Now, we know for the purposes of sound waves, at least for the purposes of our experiments, V is constant, right? It's not changing. And that is very useful to us because that means that we understand what it means when we change lambda or change frequency, because the left-hand side of the equation has to equal the right-hand side. So therefore, when lambda goes up, frequency F must go down. And when lambda goes down, frequency F must go up. So if we compare our open cylinder and our closed cylinder, right, what we've got is, for open, we've got lambda equals 2L, and for closed, we've got lambda equals 4L. So I don't think anybody would dispute me saying that 2L is less than 4L, right? So that means we've got a larger wavelength in our closed cylinder and a smaller wavelength in our open cylinder. And just as before, right, if that's a smaller wavelength, that means we have a higher frequency. And therefore down here, right, a longer wavelength will have a lower frequency. And of course we know that when it comes to frequency and pitch, right, pitch is just, what our ear perceives. Those are, directly correlated, right? So a higher frequency means a higher pitch, and a lower frequency means a lower pitch. So to sum everything up, when you blow across an open straw, you will hear a higher pitch. And when you cap the bottom end of that straw and continue to blow across the top, you will hear a lower pitch. And that's essentially what you're going to do in the lab the next time we meet. All right, thanks everybody.